Okay, thank you. I'd like to start by thanking the organizers for this chance to discuss my work. The work that I'll be talking about today was done in collaboration with three talented graduate students from Johannesburg. So that's David Gossman, who is halfway through his MSc, Lwazi Nkumani, who will nearly be finished his PhD, and Layla Tribblehorn, who's just starting her PhD. Okay. So the large N limits of matrix models remain of central importance, both to understand the strong coupling limits of non-abelian gauge theories, but also for ADS-CFT. Despite these great motivations, it's really difficult to carry out the large N limit in general. If I just give you an arbitrary matrix model, it's quite difficult to carry out large N, and if it's a multi-matrix model, we know very little. One case that we do know is when we study eigenvalue dynamics, so the singlet sector of a single matrix model. Now, why does this become so simple? Well, first of all, it's a huge reduction in degrees of freedom. So you started off with an action for a matrix. There were a total of n squared fluctuating degrees of freedom. You've gone to eigenvalues. Now there's only n fluctuating degrees of freedom. So when you perform the saddle point approximation in terms of the eigenvalues, things are immensely simpler. And in fact, the saddle point approximation in terms of eigenvalues will generate for you the large N expansion. So that's already good motivation. However, more than that, for the single matrix, it turns out you get non-interacting fermion dynamics, and that's a particularly simple system to study and explore. And more than that, this non-interacting fermion dynamics has a very clear application in the half BPS sector of ADS-CFT, the so-called LLM sector. There, the boundary conditions of the supergravity show you very clearly the non-interacting fermions that you have in your description. So basically, it looks like eigenvalue dynamics would be a very promising approach to large N in general. So the question we'd like to ask here is there a similar eigenvalue description for the two-matrix model? And if there is, does it have an ADS-CFT interpretation? So your naive answer, first of all, is definitely no. If you're integrating over random matrices and you just pick up two matrices, in general, they cannot be simultaneously diagonalized. So you cannot pick a basis where your degrees of freedom would be the eigenvalues. Nonetheless, maybe there's a class of questions that we can study, and for this class of questions, we can approach it using eigenvalue dynamics. This class of questions would generalize what we mean by the singlet sector, but now for multi-matrix cases. Okay, so I want to look back at the single complex matrix model and just think about how people got the eigenvalue dynamics. So one thing that you can do is use a Schur decomposition, which tells you that Z is equivalent by unitary transformation to a matrix D that is upper triangular. The elements on the diagonal are the eigenvalues, but you also have elements above the diagonal. Once you restrict yourself to just eigenvalue dynamics, there's a standard argument which tells you how to map the eigenvalue dynamics into non-interacting fermion dynamics. If you try to approach the multi-matrix problem using this kind of a direct change of variables, you don't seem to get very far. And basically, it's because you can't choose a basis where both matrices are diagonalized. But there's an alternative way to tackle this problem. First of all, in the half BPS sector, we know correlation functions are not corrected, so we can restrict ourselves to the free theory. And within the free theory, you can ask yourself, is there a basis of operators, basis for the local operators of the theory in the sector, that diagonalizes the free inner product? The answer is yes. They're given by the Schur polynomials. And in fact, once you've got this answer, there's an immediate link to non-interacting fermions. So the two-point function of Schur polynomials takes this form. R and S are Young diagrams labeling the operator. Each Young diagram has a total of n rows. The two-point correlator vanishes if the two Young diagrams are not identically equal. If the two Young diagrams are equal, the answer you get for the correlator is simply the product of the factors of the Young diagram. So it's a rather simple answer. Now recall that we had n fermions, and there are n rows sitting inside the Young diagram. If you take a look at the free fermion wave function that you would have obtained by direct change of variables, it's related to the Schur polynomial. You've got a Gaussian factor multiplied by a van der Monde determinant multiplied by the Schur polynomial. The wave function is an energy eigenstate. It describes n fermions, and you can talk about how much each fermion has been excited. And those excitation levels are coded directly into the row lengths of the Young diagram labeling the Schur polynomial. So now we have a map between the fermions and the row lengths, or the eigenvalues and the row lengths of the Schur polynomial. So this is what we've learned for the single complex matrix. Each row of the Schur polynomial can be identified with a fermion, which means an eigenvalue. And the number of boxes in each row tells you how much each fermion was excited. Now, if we start to consider a two-matrix model, let's consider the situation where we have many, many z's and only a few y's. In this situation, we would expect this picture to survive, at least roughly. So that looks like a good first problem to study, to see are the eigenvalues still visible in the two-matrix problem. So you can diagonalize the operators built using z and y. There's a generalization of the Schur polynomial called the restricted Schur polynomial. It's now labeled by 3 Young diagrams. One of them, R, has got a total of n plus m boxes. We have built this operator using n z's and m y's. This Young diagram R tells you how the z's and the y's are composed when we build the operator. There's another Young diagram, little r, which tells us how the z's are organized, and another Young diagram S, which tells us how the y's are organized. There's also 2 extra labels sitting here, which are multiplicity labels, and they tell us how many times this representation R, S of the subgroup Sn times Sm appears when we restrict this representation of Sn plus m to the subgroup. Once again, the two-point function is completely diagonal, and there's a rather simple factor multiplying those delta functions. There's way too many operators to think that these could be related to free fermion wave functions. And more than that, there's too many labels to associate to a free fermion wave function. So what you might ask yourself, though, is these operators don't have a definite dimension. So maybe we should be looking for operators with a definite dimension, and we've diagonalized the dilatation operator. Maybe those operators will have a better link to free fermion wave functions. Now, we can use the restricted Schur polynomials as a basis in terms of which to study the action of the dilatation operator. And we can diagonalize that action, not in general, but in the limit where the bare dimension of the operator is order n, and the number of y's is much fewer than the number of z's. The other thing that we do is we restrict ourselves to a certain number of long rows, order 1 long rows. And at large n, you find a decoupling between different sectors. So an operator with 4 long rows will not mix with an operator that has 5 long rows or an operator with 3 long rows. So we study the problem of calculating the dimensions within each of these sectors. Just to link to the previous talk was concerned with the planar limit. So you were at large n, you took the planar limit. That's a perfectly valid approach for large n, as long as you hold the dimension of your operator fixed as you take n to infinity. If the dimension of your operator scales as n when you take n to infinity, you cannot restrict yourself to just the planar diagrams. You need to sum all the Feynman diagrams. And in this situation, you don't have the powerful methods of integrability to help you. But you can solve the problem. And it turns out operators with a good scale dimension are labeled by graphs. There is 1 node for each row in the Young diagram, and directed edges connect these nodes, 1 edge for each y. So this would be an example of a picture labeling an operator with a good scale dimension. Now, what does this picture mean? So when giant gravitons were first discovered, one of the descriptions of a giant graviton that expands into the ADS space was in terms of a very highly excited eigenvalue. We've already seen that rows of the Young diagram correspond to eigenvalues. So in this case, we have 4 nodes, which means a Young diagram of 4 rows, and you should identify each node in this graph as a giant graviton. So this is some D3 brane. Now, as usual, to excite D3 branes, you have open strings stretching between the D3 branes, and each of the y's that appear on this graph can be interpreted as an open string. So we have a very clear picture where the Young diagram organizing the z's is encoded into these nodes, and the y's have become these directed line segments stretching between the nodes. You can study this anomalous dimension problem numerically. You get a certain set of answers. You can also solve it analytically, and the two approaches match perfectly. Now, we're looking for a situation where we have eigenvalues that are not interacting. In this case, you can see that these two eigenvalues certainly are interacting. There's directed line segments between them, and so would these two eigenvalues be interacting. If we restrict ourselves, however, to graphs, so we call these Gauss graphs. Okay, so we call these Gauss graphs for the following reason. Each of these nodes corresponds to a giant graviton or an eigenvalue, and this corresponds to a brane that has a compact world volume. If you study the Gauss law on the world volume of that brane, it'll tell you that the total charge on the brane must vanish, and that gives you a definite prediction. The number of directed line segments ending on any particular node must be equal to the number of line segments leaving that particular node. And if you simply solve this diagonalization problem, numerically you find that's precisely the case, and when you write the analytic solution, that's coded into the analytic solution. So for that reason, we call these labels Gauss graphs. We're now going to focus on a smaller set of operators, that is Gauss graphs, that are labeled just by graphs where the line segments leave the node and return to the same node. In this case, you can see the different eigenvalues are not interacting, they're not connected by anything, so this would be a natural guess. This is the sector of the theory that we hope you can describe using eigenvalues. In fact, this sector has a very natural description. These are simply the BPS operators. So we have a concrete proposal. If there is a non-interacting fermion description at all, it will only describe the BPS operators. And this, of course, then will mean you're being associated to supergravity solutions in string theory. So we'd like to say something like eigenvalue dynamics reproduces the supergravity of string theory. Now, this proposal was made earlier by Berenstein. He has claimed eigenvalue dynamics should be dual to supergravity. He uses a completely different argument. Berenstein's argument is based on saying, where do we expect supergravity to emerge? At strong Toft coupling. At very strong Toft coupling, the commutator squared term in the action is going to force your eigenvalues to commute. If your eigenvalues commute, you can again reduce to eigenvalue dynamics. So it's difficult to take that statement and make a very precise statement and to correct things systematically. We've started off from weak coupling, diagonalized a class of operators, and come to precisely the same conclusion. What's useful about working now at weak coupling is that we'll be able to make some analytic statements about what we're reproducing and when we reproduce them. So now I would just like to review a little bit the half BPS sector so that I can show you what's the wave function we propose in the SU2 sector. If you want to calculate some correlator that depends just on eigenvalues, you'll land up doing this matrix integral over those observables. Change variables explicitly, you're left with an integral over the eigenvalues. The measure picks up these factors of the van der Mon determinant, and you can simply interpret this as the magnitude squared of some wave function. In this line over here, you're calculating a correlation function in the QFT. In this line over here, you've basically reduced things to the quantum mechanics of n particles. So n fermions, and your goal is to find out what is that ground state wave function. Now, of course, we can do this change of variables, so we know the ground state wave function, and that's the form of it over there. So you've got a factor sitting there together with this Gaussian here, and this delta of z is the usual van der Mon determinant. The Gaussian came from the original matrix model action, so one way of viewing this is we've changed dz into the product of the eigenvalues and this delta of z. And that's some non-trivial measure coming from the change of variables. Three important observations here. First of all, there's a gauge symmetry which will allow us to swap eigenvalues. What that means is any gauge invariant quantity that you calculate will be invariant under swapping the eigenvalues. We're interpreting these eigenvalues as positions of particles, so we're saying our wave function is invariant under swapping the positions of the particles. So we're dealing with identical particles. Next thing is that if you just pick a matrix at random and diagonalize it, you'll never get two eigenvalues equal. The eigenvalues repel. So we will take these identical particles to be fermions. And that's how we understand the Slater determinant appearing in this wave function. Next, you can assign z the dimension of length. So then you can give the measure some dimension, and you can start to work out what different factors that you have here, what dimensions they should have. You can also check the scaling of z and see how the different factors should scale. And finally, we know, because these are BPS operators, that their dimensions are not corrected from the free field values, so we're going to have evenly spaced dimensions, and that tells us we should have an oscillator. For the oscillator, we would expect a Gaussian wave function multiplied by a polynomial. So in fact, if you take these conditions together, they pretty much nail down that wave function completely. Now let's try to do the same thing for two matrices. So for two matrices, first of all, we still have a gauge symmetry, but it acts simultaneously on z and y. So what we would expect at the end of the day, we've got n particles now moving in a four-dimensional space with complex coordinates given by the eigenvalues of z and eigenvalues of y. So we're still going to expect a slated determinant. We're also going to expect an association between the eigenvalues of z and the eigenvalues of y. Next, we can do the usual things, give z the dimension of length, the same as y, tells us what the dimension of the ground state wave function should be. We can scale z, leave y alone, scale y, leave z alone. That gives us an additional constraint on the wave function. And again, in this case, we have evenly spaced dimensions, an oscillator. So we again expect a Gaussian factor multiplied by a polynomial. Finally, because there's a symmetry between the z's and the y's, we expect that we should have an SO4 symmetry in this problem. So for example, if we calculate the probability density for a single particle, we would expect it only to be a function of the mod of zi squared plus yi squared. So can we write down a wave function that has these properties? And the answer is yes. That's what the wave function looks like. And what sits here is a generalization of the usual van der Monde determinant. And there's now a Gaussian factor for the z's and a Gaussian factor for the y's. Can we check this wave function in some way? So use the matrix model to calculate a two-point function of z's. You see an interesting behavior in the correlator. When the dimension of the operator is less than n, that's the form of the correlator, as soon as the dimension of the correlator is n or larger, you only get the first term, the second term drops away. And this behavior, as we increase the dimension of the operator, is going to be quite general, and we'll see it again and again. If we now calculate the same thing but using eigenvalues, so we integrate over the eigenvalue positions, there's the mod squared of our wave function. Our two observables are written there in terms of eigenvalues. You can see that what we've reproduced is the value for this operator when the dimension is greater than or equal to n. So using the eigenvalues, we correctly reproduce to all orders m1 over n, all traces of dimension n or greater. So I should stress that these are exact results, not large n results. So you're reproducing the exact result as long as you consider operators whose dimension is either n or greater than n. Because of the symmetry between z and y, we know we've also reproduced the y correlators correctly. Now it turns out we're going to reproduce correlators of a dimension n or greater. Now you might wonder, well, this is a very special trace structure, so perhaps the trace structure is playing a role. I want to give you a little bit of evidence that the trace structure has nothing to do with what's going on, and it's just the dimension. And where that evidence comes from, if you take this power to be greater than n, there are certain trace relations which allows you to relate this trace to a product of traces, some multi-trace structure. So it's really the dimension of the operator that is determining when this approximation is accurate. Now so far we've only considered traces of a single matrix. What would be far more interesting is to consider a trace where both z and y appear inside the same trace, because in that situation you would say, well, how is eigenvalue dynamics going to be able to reproduce this? We cannot simultaneously diagonalize the two operators. So we have to study a BPS operator. So to study BPS operators built with both y's and z's, we should consider a symmetrized trace. A nice way to build the symmetrized trace is shown at the bottom here. And this factor up front is just dividing by the number of terms we generate by taking derivatives. The natural proposal for what this is dual to in the eigenvalue description is the sum over I, zi to the j, yi to the k. So if we manage to reproduce this correlator, this really is quite a strong test of that we're getting eigenvalue dynamics correct. When we calculate this correlator, that's what the correlator looks like for j plus k less than n. And as soon as j plus k becomes greater than or equal to n, that's what the correlator looks like. So you can see we've got two R charges in the game, and the sum of them is the dimension, and it's again the dimension that's determining the behavior of the correlator in the matrix model. If you now look at the eigenvalue computation and you just go ahead with the wave function and calculate this correlator, you again get the exact result, not the large n result, the exact result, as long as your operators have a dimension which is n or greater. And this was a genuine multi-matrix operator. You can ask yourself, does this extend? And we've managed to calculate correlators of this type, again exactly. And the reason why I've limited myself to one dagger here is that we just don't know how to do it when there's more daggers there, but it would be interesting to check whether eigenvalue dynamics gets that correct. The thing that you need to calculate in eigenvalue dynamics is this quantity over here, and again, you get the exact result. You can also study operators of dimension of order n squared. For example, here's an operator of dimension n squared. It would correspond to an annulus in the LLM geometry. If you calculate this two-point function using eigenvalue dynamics, you again get the exact result. Now, for general Schur polynomials, you don't always get the exact result, but you do always get the correct large n behavior. And I think the reason why we're getting so many exact results here is because of the extra symmetry that you have in the ADS5 cross S5 case. We can also write down the operators dual to the Gauss graph operators that I started off motivating this work with. And for those Gauss graph operators, again, you get the large n result correctly. So now I'd like to ask, does this have anything to do with ADS-CFT, and can we see a link to ADS-CFT? Well, what kinds of geometries should we be looking at here? We're looking at BPS operators, so we're quantizing the theorem R cross S3. So we'll have an SO4 symmetry because all of these operators are built from the S wave on the S3. We've used 4 of the scalars from the Yang-Mills theory, so there's 2 scalars we haven't used, so there should be an additional U1 isometry. So we want supergravity solutions with an SO4 times U1 isometry. These have been studied by Lunan and Donos and Lin and others. And this is the structure of the geometry. The SO4 is associated to that 3-sphere over here. The U1 is associated to that circle over there. And what you notice is if you take the product of those 2 warp factors, on the y is equal to 0 plane, this vanishes. So on y is equal to 0, we're going to have to be careful with our boundary conditions to make sure that we get a regular geometry. All of the functions appearing here are determined in terms of this function z that appears. And to get a regular geometry, we need z to take the values -1/2 or +1/2. So we have a 4-dimensional space characterized by z1 and z2. And inside that 4-dimensional space, z should take the values -1/2 or +1/2. We can write the boundary condition using a surface that separates these 2 regions. So there's really a surface that determines the supergravity solution. It may be one connected surface, or it may be a number of disconnected surfaces. And we'd like to ask, is this surface visible in the eigenvalue dynamics? Well, what we expect at large n is that the eigenvalues start to trace out some definite distribution. And if we take the mod squared of the wave function and integrate over all eigenvalues except for 1, this tells us the probability distribution for just a single eigenvalue. And this itself defines some sort of a surface. So it's natural to ask, can this surface be identified with the surface that defines the supergravity solution? For the case of ADS5 cross S5, the surface defining the boundary condition for the supergravity solution is given by that equation over there. Denote the points lying on the surface determined by the eigenvalue dynamics, by Z matrix model, Y matrix model. And what you find is if you simply identify the supergravity coordinate with the matrix model eigenvalues, the eigenvalues collect on the surface that defines the supergravity solution. There's another case where we've been able to calculate the surface quite explicitly, and that corresponds to the annulus. In this case, our wave function for the annulus geometry would be given over there. This has again been tested by checking that it reproduces correlators correctly. And in this case, the supergravity boundary condition is given by that equation over there. And there's again a rather simple map between the supergravity coordinates z2 and z1 and the eigenvalues of the matrices y, mm, and z, mms. And this map is simple enough that it gives us some evidence that the eigenvalues are actually condensing on the surface that defines the wall between the boundary conditions of the supergravity solution. And I should say again that this was put forward by Berenstein, and some numerical evidence was found for this proposal. It's now that we're able to do some analytic calculations and really see that the two are agreeing. So what are the conclusions? I hope I've convinced you that there is a sector of the two-matrix model described exactly by eigenvalue dynamics. In the dual gravity, these states are supergravity states corresponding to classical geometries. The other thing is there's a nice link to ADS-CFT. The supergravity solution is defined by a certain boundary condition. That boundary condition can be given by specifying a surface, and the surface is determined by where the eigenvalues condense. So the surface is very visible from the eigenvalue dynamics. We can ask a few questions. So first of all, we've guessed these wave functions. The arguments look plausible, but you'd like to derive it and perhaps get some insight into how it is that eigenvalue dynamics works at all. Because the initial objection that you cannot simultaneously diagonalize these two matrices still holds. So you might not be sure why is eigenvalue dynamics actually giving a correct description. Then can this be extended to more matrices? In this direction, the answer is almost certainly yes, because the Gauss graphs that I showed you have been extended to include both fermions and gauge fields. So the same motivation that led us to look for eigenvalue dynamics to consider this class of supergravity geometries will exist for other more general classes of supergravity dynamics, and hopefully in the end one could include all of the dimensions that you expect from the space-time. And then finally, could you start to perturb the eigenvalue dynamics and start to include some directed line segments that stretch between these nodes? And this would correspond to starting to include some stringy degrees of freedom. Thank you.
Okay, time for questions. Yeah, then let me ask you a question. So, I mean, so your expectation is that, or at least the hope is you want to generalize this to rather general matrices and hope that it will produce some emergent geometry in the process. That's the type of the things you might want to come. Or what's your sort of ultimate goal?
Absolutely. So the ultimate goal is to really realize the dual to supergravity through eigenvalue dynamics. And at large n, the eigenvalues start to form some big structures. And hopefully these structures are what actually gives you the same structure as you get from supergravity. So that's the ultimate goal.
Oh, I see. So in this case, for example, there is an SO4 symmetry which was useful for identifying, seeing the correspondence with the gravity and the matrices.
That's right.
So I see. So in the absence of symmetry, do you have any idea how to try to match the corresponding vector and how can
Okay, I would say that even in this case, we have the first inklings of how to match. But even in this case, to show that the eigenvalues are really condensing on the supergravity surface will need a lot more work. And you could consider states that are more general. In that case, it's more difficult to carry out analytically exactly what the surface looks like, but you should be able to do it. And for every single one of these states, you should be able to map to some supergravity boundary condition. So that would still need to be done. Adding the third Higgs field shouldn't be too difficult. And in that case, again, for the ground state, it's again ADS5 cross S5. So the guess is in that situation, the eigenvalue should condense on a 5 sphere. So that case, I would say, will be quite straightforward to do. When you start to add the gauge field, well, the fermions are also not too bad. When you start to add the gauge field, I think that things become significantly more complicated, and maybe some new ideas again will be needed. But this should be enough to start studying quite large sectors of the theory.